Okay, so today we'll look at some very basic concepts of digital design, and we have looked at transistors, transistor characteristics, and so on. Today we'll kind of see how these transistors are put together to form circuits. Okay. So this is kind of a basic paradigm which I find very useful. When you want to design digital circuits, you want to keep this in mind and kind of see if you can use this paradigm. It will just help make the design of your circuits and your digital structures easier to handle. So that paradigm is essentially based on the concept of the state machine. So what you have is, you have state of the system which is stored somewhere, and then you have some computation which happens, which is a function of the current state and the inputs, the current inputs. And what that does is it updates the state as well as produces some outputs. So this is the basic model of a state machine. And since you have finite storage, you have a finite state machine. So this also is kind of at the heart of models for computing, like the universal Turing machine, which is the basic underlying model for computing. So this is kind of what it looks like. You have a state somewhere which you use to operate on the current input and also modify the state. And this, when you think of it this way, your designs, everything kind of becomes much cleaner to handle, analyze, and build. Okay. So what you have to do is you have to identify the set of states, and you have to identify this state transition. You can, maybe in your basic digital design course, you might have done the state machines and state machine diagrams. So you have a very clean identification of what are all the states, what are the state transitions, and what causes the state transitions, and so on. Then from that point on, writing the code, doing the design just becomes a routine transformation, and just expressing that in this computation block. So this is the basic paradigm which is very important for digital designs. Now let us look at a couple of examples of state machines. This is a very simple example. Okay, if I want to build a counter, what you have is here a state. Let us say it's a 32-bit counter. So there are 32 bits of state in this machine, and what you do is you take the state and produce the next state, and there is something out here which tells me, increment by how much. You can make it more and more sophisticated. You can either make it increment, or you can have a signal which says increment or decrement, increment by how much, the step, all that you can control. But basically, the current state is taken, it's modified by some operation to produce an output as well as produce the next state. So this is a very simple state machine. One important thing to notice out here is this portion, initialize or reset. So it's always important to be able to set the initial state of the state machine. Okay, otherwise you can end up with, you don't know where it's starting. Okay, so sometimes it's okay, but most of the time it's, and as a safe design practice, you always want to have a way by which you can set the state of the state machine, overriding what the computation block is doing. So it's just a good design practice. So for example, you could have just a simple signal called reset, which will just reset the state to some known state you want to put, maybe all zeros. Or you can be more sophisticated. You can actually load, you can have a 32-bit arbitrary state loaded or initialized. So it depends on how you want to do it, but it's always important to be able to override and set the state of the state machine. So from a practical design perspective, debugging, getting your chips to work and so on, it's a very important feature. So this is a very simple state machine, right? So let's look at a more complex state machine, which is a microprocessor. Okay, so in this microprocessor, there are a number of states out here. So this, if you look at the chapter 1 of the textbook, you will find a more detailed description of this particular microprocessor. every microprocessor, what it does, any microprocessor, it will fetch an instruction, it will decode the instruction, and the instruction might ask you to do some operation on some data items. So it will have to fetch the data items, do the operation, take the result and put it back in some place. Okay, and then that is basically the cycle it keeps on doing. Right? You power it on, you reset, you let it go, it just keeps on just doing that. Fetch, decode, execute, write, fetch, decode, execute, write, and so on. So you see out here the way this machine is written out here. Let's not worry too much about the interpretation of the signals right now, because for that you have to kind of read up a little bit more, and all the details are there in the textbook. But I just want to give you the high level feature and flow of the state machine, and the fact that they have written it as a state machine. So you have these things inside the bubbles are really the state variables. So they have said what the state variables are in these bubbles. And so first in the beginning there is some instruction fetch. It takes some 4 states to go and fetch the instruction in this particular microprocessor. And then when they get it, they do a decoding of the instruction out here in this state. And once they decode, they figure out what kind of instruction it is. Is it an instruction to fetch something from the memory or to access the memory? Is it an instruction to do some arithmetic operation? Is it an instruction which is saying, should I jump? Is it a branch? Right? Or there's a jump, right? So these are in this microprocessor, these are the only 4 possibilities. Of course, when you execute an arithmetic operation, there could be many possible arithmetic: add, subtract, multiply, floating point. You could have, all kinds of complex arithmetic operation. But at a higher level, these are the 4 in this particular processor. So if you come to the memory, again you can have either a load or a store, and then based on what happens, based on load or store, you decide to activate certain signals, and then you complete it. Similarly, you execute the operation and you complete it, and so on. So you see, it has become very simple to describe the operation of a microprocessor. At this level, it's like it becomes much easy to describe and design this machine. And then now you can progressively go down, and you can start adding complexity for different executes and so on. So now one thing you notice in this thing is that a need for what is called sequencing. That is, there is a notion of something happening after something else. There is a progression of events, right? There is a progression of computation, and you need to kind of maintain this coherency. You have a bunch of signals, which all kind of bundle of signals, which are all related to that particular step of the computation. For example, a 32-bit counter, you read the counter value, all 32 bits have to come about the same time, and you have to process them together. If one of the bits comes a little early and later, and you cannot process it independently, then it will be a mess, right? So you have to maintain the coherency of the signals. You have to maintain this temporal sequencing, and there are 2 ways of doing it. There is the synchronous approach and then asynchronous approach. In the synchronous approach, what you have is you have a global clock. The clock is a periodic signal, and all activities are synchronized with the edges of the clock. So that is the synchronous approach, and that is pretty much the dominant design style right now for digital designs. Almost all designs are done in a synchronous way, and this course also will be pretty much focusing on synchronous design. In the asynchronous approach, there is no concept of global clock, but somehow you still have to maintain the requirements of order and coherency and so on. You can't get away from it, but there is a different way of achieving it in a very distributed manner, and it's kind of somehow implicit in the kind of delays which are there. Some local triggers are generated and so on. So most man-made designs, man-made computing units are basically synchronous. All biological computing units are asynchronous. right? See our brain. There is no global clock, okay, which is triggering an activity. It's asynchronous, but it's doing remarkably complex computation. So asynchronous, and it's really low power, like the most power efficient, energy efficient computing engine we know. So asynchronous is kind of very intriguing and promising from that perspective, but we haven't figured out yet how to build very large asynchronous machines. Okay, so you take that, and then you kind of, when you get down to the next level of implementation, you have the state machine description. Now you get to the next level of implementation, and here's what happens. You have basically a control unit which is keeping all the states in the control units. This blue box has all the state bits coming out of here, and then they go and then they kind of control the way computation is happening, and then their outputs are sometimes also basically used to update the state out here. Okay, sometimes some of these outputs go and update the state. And if you notice out here, these the computation itself can happen over multiple cycles. Okay, it's not that it needs to finish in one cycle. It can happen over multiple cycles, and that is again sequenced using this clock signal. CLK is a clock signal. It is a global signal. That means the whole chip everywhere you get the same clock signal. It's required that the clock appears at almost the same time throughout the chip. And these blocks are the what are called flip-flops or sequencing elements, and then you have some computation happening out here. This is a register file. This is the ALU, and then you store the data, and then so on. Okay, so you see basically there are two kinds of elements out here, for circuit design elements. One is the logic gate out here, which forms this multiplexers, adders, subtractors, etc., and other things. And then you have the sequencing element, so which stores state, and those are also out here in this block, which stores the state. So let's basically see how you would design each of these basic building blocks to so that you can then construct your digital engine. So first let's start with the logic gate. And this is the template for any CMOS logic gate. There is a pull down network and a pull up network, and they are duals of each other. We'll see what a dual means. And really the important point out here is, if you look at this table out here, the output states of the CMOS logic gate. When so you have each of the pull down and pull up network can be on or off. What do we mean by that? By that, on means there is a path from the output to either VDD or ground. Off means there is no path. There is no connectivity, because remember these are all switches. We are using them as switches. So when pull up and pull down both are off, the output is not connected either to VDD or to ground. Okay, when that happens, the output we say is floating, and that is denoted by the symbol Z. Z also stands for high impedance. That means when you look from here into the gate, there is no low impedance path to either the VDD or ground. Both paths are high impedance. It's almost infinity in an ideal case, but essentially it's a high impedance. That's why it's called a high impedance state. Of course, when pull up is on, pull down is off and pull up is on. Pull down is off, pull up is on. There is a low impedance path from output to VDD, and output is at high, and vice versa. Of course, the problem comes when both are on. When both are on, it's called X or crowbar. X means, so we don't know where this voltage will be. It really depends on the relative strengths of the pull up and the pull down. It could be anywhere. If they are equal strengths, remember from the DC transfer curve, if pull up and pull down are equal, the voltage will be exactly in the middle. So the next stage will not know whether it's a 0 or 1, so that's why we call it an X. Also, there is a lot of current. This current is called the crowbar current. So there is a current from VDD to ground because both are on. Now, when we design CMOS logic gates, we design the gates as that these pull up and pull down networks are duals of each other. When that happens, you are guaranteed that both, you are always in one or the other state. You are not in this state. Okay, so that is the idea out here of having duals. So let's take an example. So NAND2 gate. So we have a truth table A, B. So you have, when in a NAND, y is equal to A dot B bar, only when A and B both are 1, we want the output to be 0. Which means only for this condition the pull down is on and pull up is off. For all others, pull down is off, pull up is on. So this is the structure out here. A, B is high, only for that case the pull down is on. So Y is connected to ground. And then also for the same case, because A and B both are high, the PMOSs are off. So there is no path to pull up. For any other signal, when even if one of A or B is 0, the corresponding PMOS will be on and that NMOS will be off. So the series path is disconnected, the pull up path is activated. So this gives you the NAND structure. 2 here signifies a 2 input. It's a 2 input NAND gate. You can have NAND 3, NAND 4, NAND 5, NAND etc. etc. Okay, so this 2 is also called the fan-in of the gate. What is the fan-in? How many inputs are getting connected or coming into this gate? Okay, so that's why it's called a fan-in. Think of a cone, inverted cone, where the cone has a wide opening and then a narrow exit, right? So that is why it's called a fan-in. Similarly, an output of a gate can be connected to many other gates. So the number of gates it gets connected to is called the fan-out. So that is the definition of fan-in and fan-out. Typically, we cannot say what the fan-out is because it really depends on how you use the gate. But we can say what the fan-in is. Clearly, it's just 2. Fan-out, we don't know. It could be 1, it could be 4, it could be 8, etc. So that is another, since you raised this point, in comparison with a biological system like a neuron, in these systems, our systems, fan-ins are usually maybe 4, 8, 10, and there are special cases where you could have large fan-ins in memory structures and so on, maybe 128, perhaps, maybe 256, perhaps 1000, okay, but that's about it. But in biological system, easily you have 10,000, fan-in of 10,000, fan-out of 10,000, like that. So each neuron has huge capability of connecting, and you have very rich networks which are possible. So the NMOS switches, right? So you have only when you have 1 and 1 is A connected to B, otherwise it's off. Similarly, for the parallel combination, when either of them is 1, A is connected to B. In the case of PMOS, only when only when both are 1, it's off. So this switch based logic is important. Why? Because when someone tells you, okay, implement this particular function in a CMOS gate, okay, that will be a question for you in one of the quizzes. So I'm telling you right away. Okay. So how do you do it? So you basically find out the switch network for the NMOS. Once you find it for the NMOS, for the PMOS is just the dual of it. Okay, and then you put the two together and just cross check your answer always. Okay, just check if it's, especially the truth table, just see if all the values, when you put in those values, are you getting the right outputs or not. Okay, let's take the example of the gate y equal to A dot B plus C dot D. So intuitively, what is this? How do you go about it? You know that when either this or this is 1, output is 0. So that means immediately, so first start off with the NMOS. At least I start because it's easy for me to think of NMOSs than PMOSs. Okay, so that means I have somehow 2 parallel paths. Either this path gets activated or this path gets activated. When either of them gets activated, output gets connected to ground. So immediately I know that there are 2 parallel paths. Now let us take this particular path itself, A dot B. That means A and B both have to be high. Only then this is high. That means there is a series connection of two transistors in that path. So similarly, C and D, series connection. Okay. So now this is what we get. Pull down is a series connection of A and B, C and D, both of them have to be in parallel. So this becomes my pull down network. Once I get my pull down network, pull up is just a simple algorithmic transformation. Okay, you can apply that. I mean, you can also again start and try to think for PMOSes and so on, but it can, unless you are comfortable working with the complements, it can kind of become a little different. It's much easier to just do this simple algorithm, which is any series transistors you connect to a parallel, and any parallel becomes series. Okay, so what you have is the following. So now we are concerned about the PMOS. So in this group, A and B are series, so they become parallel for the PMOSes. Okay, this group C and D are series, they become parallel. And then these two groups are in parallel, so these two groups will become in series. That is the simple approach, and then you put it together and you get this gate. Now this is called a AND or invert. 2-2. Okay, that's what it's called. That means there is an AND gate in the beginning, followed by an OR gate, followed by an invert. So it's an AND or invert. Now this same, you could kind of implement this gate using these specific ANDs and ORs. But here it's been done in a single stage. It's called a compound gate. This compound gate is much more compact as opposed to a gate like this. Okay, we'll just see that in a couple of slides, and I'll come back to this. So this is how we design CMOS gates. Okay, you have the truth table. From the truth table, you figure out what conditions or what is the Boolean equation for y is equal to something. A CMOS gate is always inverting, right? You always have a bar in the top, because when inputs are all high and the pull down is activated, output goes to 0. So it's an inverting gate. So then once you have the logic equation, then it's just applying this series, parallel, get the NMOS stack, then do the dual to get the PMOS stack, then cross check the truth table, are you getting it? If you get it, then you are done with the design of the gate, right? At least the template of the gate. The second aspect of the design is the sizing. So that will come to in the succeeding lectures, but at least you get the topology of the gate. Now you can use these transistors not only to connect an output to ground or VDD, that is either in pull up or pull down, but also to in some sense control the flow of signals between gates. Okay, for example, if I just have a simple transistor, NMOS transistor, say I have one logic gate here, another logic gate here. This transistor can act as a gatekeeper. When G is high, it will allow S to connect to D. It will allow whatever is here to talk to this person. When G is low, it will not allow it to talk. Except there is a problem. What is the problem? When G is high, clearly when G is 0, this is disconnected. So this person will not be able to talk to this person. When G is 1, yes, they are connected, except the connection is good for 0, propagating a 0, but not good for propagating a 1. Why is that? Right. So what happens is, let us think of the situation where G is 1 and this S goes to VDD, logic 1. Okay, and now SD also starts charging up. Okay, because G is high. Now which is the gate in that situation? Which is the gate? Which is the source? It's labeled S and D here, but really the current flow is like this. If S is VDD, I mean this left side is VDD, the right side is ground, and the charge will flow like this. So really the node labeled D is actually the source. So what is the current drive given by? It is given by the potential between G and the source. To begin with, source is 0, gate is high. So you have a very good gate overdrive. Gate to source voltage is VDD, threshold voltage is VT. So VDD minus VT, that is the overdrive, and you will get a good current. You will have a onrush of current. But as this node starts going up, you see that this gate overdrive starts dropping. It's like a self-limiting. phenomena. It starts dropping till this reaches a threshold below this. As soon as it reaches a threshold below this, say VDD minus VT, the gate overdrive becomes 0. Right? VDD is this, with this VDD minus VT, so the difference of the two minus VT is 0. So there is no more gate overdrive, there is no more current. Okay, if you assume the long channel model. So really what happens, it charges to VDD minus VT and stops. It really doesn't go all the way to VDD, so you have a degraded one. It's not good for noise margin. Maybe the next gate might not consider it to be a proper one. If there is a little bit of noise, it might consider it to be in the no indeterminate region or perhaps even a 0. So passing a 1 through a NMOS is not a good idea. Okay. But passing a 0, there is no problem. When this is 0, let us say the left side, the right side is VDD, then what happens is he just discharges. This 0 remains 0, VDD just discharges. Even though the drain is reducing, the gate source voltage, nothing is happening to it. It's remaining fixed. So you have a nice clean drop all the way to 0. So passing a 0 is okay, passing a 1 is not very good with an NMOS. So that you should remember. Okay. If you think of a CMOS gate and in the pull down stack, in some sense we are passing a 0, we are passing the ground to the output. So there is no issue. I mean, this applies even for stacks of NMOSes. I mean, we are showing this for a single NMOS, but if you can arbitrary network of NMOS gates, series, parallel, all kinds of combination, you'll have the same problem. That is, one will not be passed very properly from the left to the right, 0 will be passed. The other thing you should notice here is that there is nothing sacrosanct about passing from left to right. I mean, I can also pass from right to left. This is a bidirectional structure. Okay. Now, whereas in the CMOS gate, in some sense, there is a flow of signal from the input to output. Here, it can go either way. Depends on who is on both sides. So sometimes it can be a problem. Okay, we'll look at, there are situations where you have to really watch out for this. You didn't intend it to be like that. You wanted signal to go from left to right, but this is just a pass gate. It can go even from right to left, and sometimes it can lead to all kinds of problems. Now, the PMOS has the opposite problem. In the case of PMOS, it passes a 1 very nicely. That's why we use PMOS for the pull-ups, but it doesn't pass a 0 properly. Why? Let us say, so let us say the output is the input is 0. Okay, the output D is VDD, and the gate is also 0. Okay, so that means the current is flowing from right to left. S is 0, D is high, and there is a large gate to source voltage because gate is 0. This is high, so there is a large gate to source voltage. But as it starts discharging, just like in the case of NMOS, the gate source voltage starts dropping, and it really starts limiting the current. And when it reaches a threshold above ground, it just stops. Okay, and so it doesn't. Beyond that point, it doesn't drop, or it drops rather very slowly. Why would it drop very slowly? Because remember, in reality, you never have a transistor which is fully off. There's always some leakage current. So even in the case of NMOS, it will reach to VDD minus VT quickly, but after that, it will take a while for it to reach to VDD. Okay, because there's always some leakage current it will charge it, but it's so slow that for practical purposes, you can say it doesn't go fast. So how do you fix this? You fix this problem because there are a lot of places where you need to use this kind of a structure of passing and controlling a signal flow. Okay, for that you use what is called a transmission gate. That means you pair up a NMOS and a PMOS in parallel. NMOS is good in one thing and bad in the other, and PMOS fortunately is exactly the opposite. So you pair them up together, so they are good in both. So here you see the gates are complements of each other. So when you have G is high, the PMOS gate is given low. So both are on at the same time. So now it doesn't matter. If I want to pass a 1, PMOS takes up the brunt, or helps to pass a 1 properly. If I want to pass a 0, the NMOS helps pass a 0 properly. So both are handled properly. These are the various symbols which are used. Different people use different symbols. So for the transmission gate. So when you don't know what logic value you want to pass, in the sense that maybe sometimes it's 0, sometimes it's 1, then you should use a transmission gate. Right? That is a parallel combination of NMOS and PMOS. But there are cases when you know for sure that if you want to pass something, it is a 0 or a 1. Then you can be a little bit more stingy with, you can say, okay, let me remove 1. If I know I'm always, if at all I pass anything, it is a 0, you can remove the PMOS and just leave an NMOS, because it helps you to reduce the area and power and so on. But if you don't know, you want to use both. So this, we saw a CMOS inverter which consisted of a PMOS in the top, pull up, and NMOS in the pull down. What if you were to reverse it? What if you were to say that, look, I'm going to put a NMOS in the top and PMOS in the bottom, then I will get a non-inverting buffer. Okay, sometimes buffers are good. You want to maybe increase the drive strength and drive and so on. So you want to drive a large load and you want to have a larger drive strength, so you put a buffer. But this kind of buffer is bad because it neither passes a 1 properly nor a 0 properly because of the threshold dropout here. So you should not be doing this. If you want to really build a buffer, what will you do? You put 2 inverters in series, one after another, right? So that's basically what you do to build a buffer. So now if there is a particular logic function, we saw AND or invert or NAND2, NAND4 and so on, there can be multiple ways of realizing that. Okay, for example, let us take the NAND4 gate. That means it's a 4 input NAND gate. So one approach is what? Say here, for example, it's a 4 input AND function. I can do it this way. I can have a NAND with an inverter. If you notice out here, it's a funny style of writing the inverter, right? So inverter is a triangle, but the bubble, instead of being in the output, has been put in the input. Why? Just so that when you read it, it becomes very clear, because these two bubbles will cancel each other. So you know it's just a AND followed by a buffer, so it's an AND gate. So just for user readability, for you to quickly see what the function is, this is kind of done. Okay. So similarly out here, if you see, again it's very clear. This bubble will cancel this bubble. So it's implementing the same logic functionality. Similarly out here, you see this bubble, these two bubbles will cancel each other, right? And so again it's the same functionality. What is this gate? It's a NOR gate, right? Because it's really a NOR gate. NOR gate has a OR followed by a bubble in the output. You push the bubble in, essentially apply De Morgan's law, it converts into a AND with an inversion at the input. So now you have these possibilities. For example, let us take this and this. Here what you are doing is that you are implementing a 4 input NAND gate. We saw a 2 input NAND gate. It had a pull down stack of series stack of 2 NMOSes. A NAND4 will have a pull down stack of 4 NMOSes and a pull up of 4 parallel PMOSes. So that could be one way to do it. Or you could do it in this way, where you have already built a NAND2 gate, you cascade a NAND2 gate, you build a NOR2 gate, you cascade. Okay, so the question is, which is a better way of doing things? Okay. That answer will come to, that is part of the so it's more of a rhetorical question, not asking you, but really that is part of the design problem. How do you figure out which is the better approach to do? Let us take the AND or invert also. We already saw the single stage implementation, right? It's a compound gate called a compound gate. And really it is AND or invert. So I can also implement it as literally like this. I take this AND gate, which I implement consists with a NAND and an inverter. Remember, any CMOS gate has to be inverting. So you always have a bubble out of a CMOS gate. So you have a NAND with an inverter to give me the first AND, this NAND and inverter to give me the second AND, and then these two I can make it into a NOR by putting a NOR inverter. I guess I could have removed this. They could have removed this inverter. These two inverters would have been enough. But anyway, they put these. Okay, so this is basically a multi-stage implementation of the same structure, similar to the NAND4. So one of the questions is, which of the two approaches better? Clearly between these two you see, as many of you pointed out, that this seems to be very compact, right? There are basically 4 plus 4, 8 transistors, whereas here a NAND2 itself has 4 transistors, right? An inverter has 2, that is 6, 4 plus 2, 6 plus 6, 12, plus another 4, 16. So let's ignore these two inverters. Suppose we were to optimize. So you have 16 transistors, this is 8. This has twice the number of transistors. So then the question is, why clearly no one builds one, you can take a whole combinational circuit and build it into one humongous gate, right? People don't do that. So there is a point at which you say, look, enough complexity in a single gate, now I really need to cascade gates. Okay, so there is a kind of point at which a single gate becomes kind of complex and slow, and it's better to have multiple gates. Okay, and and that's really got to do with the fan-in. When the fan-in of a gate becomes larger and larger, okay, so that means a series stacking. If here I have a series stack of 2, whereas a series stack of 4, it turns out, is kind of really pushing it. The gate becomes quite slow because you have 4 series transistors. Imagine each transistor is a resistor. Okay, with each resistor there is a small capacitor also. So the delay of a circuit, you can think of it intuitively as an RC product. So if I have n stages, n series stages, each stage offers a resistance and some amount of capacitance. So the total resistance grows as a function of linearly with n. Capacitance also grows linearly with n. So the RC delay grows as n square. So that is where the problem comes. When the series stack starts increasing, the delay starts degrading quadratically. So very rapidly the delay decreases. So you don't want to have too large a series stack. So usually the series stacks in gates are limited to 3, perhaps 4, but 3 and less. Okay, so if you find that you need to get to a 4 stack gate, you say, okay, maybe I need to break it up into 2 gates, and then you do it there. Just a note on terminology, you might find these notations here, AOI22, which is AND or invert 2-2, which is basically AND, OR, and then invert. And 2-2 is saying how you partition the inputs. 2 inputs here and 2 inputs here. Whereas OR and invert 3-1 means I have a OR and a and 3-1. That means this one has 3 and the other one has 1. So that's basically the notation being used here. So basically you have, just to repeat the terminology, explanation for the terminology, AND or invert means first I have an AND function, then followed by an OR function, then an inversion. Okay, and then we are having 2-2. It's a 4 input gate. The first stage is an AND gate, set of AND gates. So I have, and the way I break my inputs is 2 inputs to the first AND gate, 2 inputs to the second AND gate. So I have AND stage or stage. So, and it's 2-2. That means I put 2 inputs here, 2 inputs here. OR and invert means first stage is all ORs, second stage is AND. And OR means, and then they are, and it's 3-1. So the first OR gates get 3 inputs, the second OR gate gets 1 input, which means I might as well not have the OR gate also, right? I mean, it's just, you can just remove it, and so you have this kind of a structure. Yes. This is also giving you the sequence. The first stage is an OR, second stage is AND. So the question is, what is the difference or the contrast with this notation called the sum of products and product of sums and so on. So you see out here, right? This is the sum of products. This is the product of sums. So essentially, you have AND or AND is kind of really capturing that. So in that sense, they are kind of mirroring each other. But sum of products and product of sums is a kind of more general notation. In general, any Boolean function you can write it that way. Here we are, just talking about one very specific gate. So the number of inputs are restricted, but there is an analogy, just a different notation for that. Plus, these gates also are inverting, whereas sum of products, product of sums, there is no inversion explicitly at the output. Here is another useful gate. So we have seen the basic template of a CMOS logic gate. We have seen pass transmission gates, and then now you have the tri-state inverter. What is a tri-state inverter? It's an inverter, except it also has the additional capability of going into a high impedance state. That means both pull up and pull down are left disconnected. So output is high impedance. It's kind of floating. We don't know which value it is. So you might ask, why is that useful? Before getting to that, let's just see how it works. So you have, what you do is, you take a simple inverter. Okay, to that you add these two extra transistors, one in the PMOS and one in the NMOS. So you have two series NMOSes, two series PMOSes. Except the inner ones are controlled by this enable signal. So when enable is high, this NMOS is on and enable bar is low, means PMOS is on. So both NMOS and PMOS are on. So effectively, it's like a simple inverter. So whatever happens to A, the complement happens at Y. But when enable is 0, this NMOS and this PMOS both are off. So no matter what happens to A, Y cannot be connected either to VDD or ground. So it's just left hanging, high impedance state. Okay, that is called by Z. So this and these are the symbols out here, So there is an inverter with either a single or two of these kind of thing. Just to denote that it's a tri-stateable inverter. This is useful for building multiplexers. So you could have multiple of these signals all connected to the same output, and you want to activate only one of them. All the others you want to leave it in a high impedance, because if multiple of these are on at the same time, there will be fight. This is typically useful for buses. You have buses with multiple, people who want to put information on the bus. You have to ensure that exactly one person is on and putting information on the bus. Can you repeat that question? So let me see if I understand the question. The question is, here should there be a single transistor or two transistors in parallel? Is that what you're asking? Yes. So the figure D, the question is, what is happening out here? Okay, why isn't there another little thing sticking out? I don't know the answer to that, why the author has drawn it this way. Perhaps maybe it's implicit that you have both, just so that you don't clutter this. Maybe it's assuming that when you have something like this, you have both enable bar, perhaps that. Or maybe he's also thinking of a situation where there is a tri-state capability only in the pull up and not the pull down, perhaps. So I don't know. So, but you can build multiplexers, so you could also build multiplexers using pass gates or transmission gates. See this transmission gate out here, so this is a 2:1 multiplexer. So when S is high, the lower NMOS is on and S bar is low, that means this PMOS is on, so this transmission gate is on, whereas this is off. And so D1 is connected to Y, and when S is 0, D0 is connected to Y. So it's a 2:1 multiplexer. Okay. Now the same multiplexer can also be built in multiple ways. You can think of it as a you can write the truth table, and then you can work out the the pull down and pull up stacks, and you can kind of get something like this, compound gate like this, or you build it using what we just saw, tri-state inverters. You have tri-state inverters where S takes on the role of the enable. So to one of them you give the S as the enable input, the other tri-state you give S bar, and so one or the other is on, the other is put in high impedance. So you could even build it this way. So multiple ways of building a multiplex, 2:1 multiplexer. So what is the, and see, this is an inverting multiplexer, right? Because it's built like this, it's an inverting multiplexer. There is a bubble here, whereas this is a non-inverting multiplexer. So NAND, once you can build a NAND gate, a NOR gate, or a multiplexer, you can basically, even if you can build one of these three, each of this by itself is a what is called a universal gate. You can build all Boolean functions using these gates. So any complicated Boolean function you can build using cascades of these gates with appropriate inputs to these gates. So we have seen logic gates now. We have seen how to build compound gates. Now let us look at so we know how to build the computing engine, right? The computing engine, whatever logic you want to implement, adder, subtractor, whatever it is, decoding, all using logic gates. Now we know how to build. Okay. So let us look at the sequencing elements. First we'll start with the latch. Okay, typically most synchronous designs use flops. Okay, but a flop is built out of a latch. So first let's look at a latch. Of late, new designs are coming, and there are some advantages to use latches in design, but we'll kind of cover that later in the course. For now, let's just first look at a latch. A latch is something which is really, the analogy is this door. When I leave the door open of the classroom, we say it's in a transparent state. People can easily come in. Outside the room is the input, inside the room is the output. Suppose we define it that way, then whatever happens in the input, it can pass through and come into the output. It's an open door. As soon as the door is closed, so when the door is open, we call it transparent. And when door is closed, it is opaque. What happens outside cannot influence the inside. So that's basically what the functionality of the latch is. So what you have is, this latch is transparent when the clock is high. Okay, when the clock is high, it's transparent. We'll come and understand this circuit first, but before, let's look at the waveform. When the clock is high, it's transparent. What that means is that during the portion clock is high, whatever happens at the input shows up at the output. So as soon as clock goes high, the input is high. So the output of the latch, which is Q, goes high because it follows the input. After some time, what happens? D goes low. So output also follows. So any wiggling in the D here, Q will mimic that. As long as clock is high. As soon as clock goes low, D cannot influence Q. D has gone high, but Q remains zero. So the last value of Q is what happened just at the point clock went low. That is like the capturing input. As soon as at the instant clock went low, whatever was D, that gets frozen in Q and remains there till the next time the latch becomes transparent. How is the latch implemented? In this fashion, this is one way. Say this is a 2:1 mux and you have these inverters. So when we say clock is high, the mux connects the one input to the output, right? So D gets connected here. This input is not connected. So this gets connected here and then it goes out. So whatever happens to D also happens to Q and then Q bar. So you see it's transparent when clock is high. As soon as clock goes low, the mux switch gets switched to this. So only this input goes. So you see now there is a recirculation happening. Whatever Q is there becomes Q bar, which gets inverted to the same logic value of Q and gets reinforced. We saw this in the DC transfer curve lecture, this feedback, back-to-back inverters, it retains the state. No matter what happens at the input, the mux is off. It cannot, mux will not allow D to get propagated to, so it holds the state. So this is a latch. So this mux can be built in many ways. We saw already using transmission gates you can build a mux, with the enable being the clock. So this is one way of building the mux. Okay, and these two are just kind of explaining the operation of the mux when clock is high and clock is low. So this is the concept of a latch. Now as I said, most synchronous design uses flip-flops. Flip-flops are edge triggered. Really, the analogy for a flip-flop is a camera. When you press the click button, the shutter opens, captures the image. That's it. There is no transparency, opaqueness, nothing. Just for that instant, when you press the trigger button, it will click the image. So that's basically what a flip-flop does. Flip-flop can be positive edge triggered or negative edge triggered. You still have the clock. The clock edges define the clicking action of when it captures. In a positive edge triggered, the positive edge captures the data. So whatever is the data in the vicinity of the positive edge, that gets captured and given to the output. And now you see data changes here and here, nothing happens. The output doesn't change. Only the next positive edge, whatever is again at the input, gets sampled and given to the output. So it's an edge triggered flip-flop. So latch is there and flip-flop is there. We have to distinguish the two. Sometimes in a loose way people kind of use one or the other, and it can become very confusing, because latch has a transparent phase, opaque phase. Flip-flop is like a camera. There is an edge triggered, either positive edge or negative edge. Okay, and you build a flip-flop using two latches. And you give clock and clock bar like this with an inverter. This is called the master latch, this is called the slave latch. Okay, let's see how that works. So here you have the master latch, here you have the slave latch. So what happens is that, let us say the clock is 0. Okay, when clock is 0, I think it's easier to probably understand this figure out here, the lower figure. When clock is 0, the slave latch is opaque, whereas the master latch gets a 1, right? Because its clock bar is given, so it's 1. So master latch is transparent. So when clock is 0, master latch is transparent, which means whatever is happening to D comes to QM. QM is kind of is following D, but it doesn't come to Q. Q is isolated. As soon as clock goes from 0 to 1, the master latch goes opaque. So whatever was there in D gets frozen in QM, it remains there. But then the slave latch becomes transparent, and so QM comes out to Q. So you see how with these two master and slave latches you are able to capture the data. And now when clock is high, that means slave is transparent, but master is opaque. So this input cannot come to the output. So you are only taking the data at that particular instant around the vicinity of the clock edge. Okay, this is how the positive edge triggered flop works. If you invert the polarities and give it, then it becomes a negative edge triggered flop. So the same concept is being explained here.